A lithium-ion battery can sit quietly in your phone for years. Then, under the wrong conditions, the chemistry inside can begin feeding its own fire. The strange part is how quickly a stable battery can become an unstable one. To understand why, we have to look inside. A typical lithium-ion cell contains two electrodes separated by a very thin barrier. Lithium ions move between those electrodes while the battery charges and discharges. Electrical energy comes from controlling that movement. But the same compact structure also stores a substantial amount of chemical energy. Normally, several layers of protection keep that energy under control. The problem begins when something pushes the cell beyond the conditions it can safely tolerate. That could involve severe overheating, physical damage, manufacturing defects, or an internal electrical short. An internal short is especially important because it can create a concentrated source of heat inside the cell. At first, that heated region may be tiny, but heat changes chemistry. As the temperature rises, some internal materials can begin breaking down. Those reactions can release additional heat. Now the battery has a dangerous feedback loop. More heat drives more reactions. More reactions generate more heat. And the process can accelerate rapidly. This runaway process is called thermal runaway. The important detail is that the battery does not need an enormous external flame to begin this process. The critical event can happen inside the cell itself. As internal temperatures continue rising, the separator can lose its ability to keep the electrodes apart. That can create additional electrical contact, which can produce even more localized heating. The feedback loop becomes harder to stop. Meanwhile, heat can also cause internal materials to release gases. A sealed cell has limited space for those gases to expand, so internal pressure can rise. The casing may swell or deform. If pressure becomes severe enough, the cell can rupture. At that point, hot gases and reactive materials can escape. If those materials encounter suitable conditions, ignition can follow. That is why a battery failure can appear sudden from the outside. The visible event may be the final stage of a process that started internally. And there is another important detail. Lithium-ion batteries do not all behave identically. Their chemistry, construction, size, condition, and operating environment all affect how they respond to heat and damage. So there is no single temperature at which every lithium battery suddenly explodes. The exact behavior depends on the cell and the conditions around it. This is also why the phrase battery explosion can hide several different physical events. Sometimes the main event is gas release. Sometimes it is fire. And in severe failures, rapid pressure release can damage the surrounding casing. The common thread is the same chain of physics and chemistry. A small internal problem changes the temperature. Higher temperature changes the chemistry. The chemistry releases more heat. That extra heat accelerates the process. Eventually, the energy release can become much faster than the battery can safely dissipate heat. That imbalance is the key. A battery can remain stable while heat is removed quickly enough. Once heat accumulates faster than it leaves, the internal temperature can climb. That is the moment the system can move from stable to runaway. The surprising part is that the battery does not suddenly gain energy from nowhere. The energy was already stored inside its chemistry. The failure changes how quickly that energy is released. A controlled battery releases energy through an electrical circuit. A damaged battery can release part of that energy through unwanted chemical and thermal pathways. That is why the same compact object can be harmless during normal operation and extremely energetic during a severe failure. Modern battery systems therefore use multiple layers of protection. These systems can monitor temperature, electrical conditions, and charging behavior. The goal is to keep individual cells away from dangerous operating conditions. But no protection system can make every failure physically impossible. Severe damage, defects, or extreme conditions can still overwhelm the system. And that brings us back to the original question. Why can a lithium-ion battery suddenly explode or catch fire? Because under severe conditions, heat can trigger reactions that create more heat. Those reactions can generate gases, increase internal pressure, damage internal barriers, and accelerate the failure. From the outside, it can look like a sudden explosion. Inside, it is a chain reaction that has been building through the cell. The battery did not suddenly become dangerous because it contained some mysterious new energy. The danger came from a change in how that stored energy was being released. And once heat production begins feeding itself, a quiet battery can become a very different system. That is the physics behind the sudden failure.